A black hole is one of the most extreme objects in the universe, not because it is a hole in the ordinary sense, but because it represents gravity pushed to its absolute limit. When most people imagine a black hole, they picture a dark opening in space, a cosmic vacuum cleaner that swallows everything nearby. The reality is both more subtle and far more profound. A black hole is not an empty void. It is a region where matter has been compressed so densely that the curvature of space and time becomes overwhelming. Gravity there is so intense that once something crosses a boundary called the event horizon, it can never return. Not even light can escape, which is why the black hole appears black. The event horizon is not a physical surface. It is a mathematical threshold, the point of no return in space-time itself. Outside this boundary, the laws of physics behave in ways we can still describe. Inside, our understanding begins to fail. Black holes are born from the collapse of massive stars. When a star many times heavier than the sun reaches the end of its life, it runs out of fuel. The outward pressure that once balanced gravity disappears, and the star collapses inward under its own weight. In the most violent cases, the outer layers explode outward as a supernova, while the core continues collapsing until it becomes something unimaginably dense. If the remaining core is heavy enough, nothing can stop the collapse, and a black hole forms. This process creates stellar mass black holes, objects with masses several times that of the sun, packed into a region smaller than a city. But black holes do not only exist as the remnants of stars. At the centers of galaxies, including our own Milky Way, lie supermassive black holes with millions or even billions of solar masses. Their origins are still one of the great mysteries of cosmology. Somehow, in the early universe, black holes grew to enormous sizes, shaping the galaxies around them. Yet despite their terrifying reputation, black holes are not cosmic monsters roaming the universe. Most black holes are quiet. They do not actively consume matter unless something ventures too close. From far away, a black hole's gravity behaves like the gravity of any other object of the same mass. If the sun were replaced by a black hole of equal mass, Earth would continue orbiting almost the same way. The difference is what happens when matter approaches the black hole closely. Near the event horizon, gravity becomes extreme. Tidal forces stretch objects dramatically, a process sometimes called spaghettification. Time itself slows down relative to distant observers. According to Einstein's general relativity, gravity is not simply a force pulling objects together, but a curvature of space-time. Massive objects warp the geometry of space and time, and black holes represent the deepest possible curvature. As you approach a black hole, the flow of time changes. To a distant observer, an object falling toward the event horizon appears to slow down, never quite crossing it. The light from that object becomes redshifted and fades away. But for the falling object itself, time feels normal. It crosses the event horizon in a finite moment, and beyond that boundary, the future points inevitably toward the singularity, a point where density becomes infinite and the known laws of physics break down. The singularity is not something we fully understand. It is a sign that our theories are incomplete. General relativity predicts it, but quantum physics suggests reality cannot truly become infinite. Somewhere inside black holes, a deeper theory must exist, one that unites gravity and quantum mechanics. Black holes, therefore, are not only objects in space, but laboratories of extreme physics, places where the universe reveals the limits of human knowledge. They challenge our understanding of matter, time, and the structure of reality itself. One of the strangest aspects of black holes is that they distort not only space, but the very meaning of time. Near a black hole, time dilation becomes profound. Clocks closer to the event horizon tick more slowly compared to clocks far away. This is not an illusion, but a measurable consequence of gravity. In extreme cases, if you could hover near the event horizon of a supermassive black hole, you might experience hours while centuries pass for the rest of the universe. This makes black holes deeply connected to the nature of time itself. They are cosmic reminders that time is not absolute, but woven into the geometry of space-time. Black holes also produce some of the most energetic phenomena in the universe. When matter falls toward a black hole, it does not simply disappear quietly. Often it forms an accretion disk, a swirling structure of superheated gas and plasma orbiting at near light speeds. Friction and magnetic forces in this disk release enormous amount of energy, sometimes outshining entire galaxies. Some black holes launch relativistic jets, beams of particles traveling close to the speed of light, extending for thousands or even millions of light years. These jets shape the evolution of galaxies, influencing star formation and the distribution of matter. In this sense, black holes are not merely destroyers. They are also architects of cosmic structure. They regulate galaxies, sculpting the universe on the largest scales. Yet black holes remain invisible directly. We detect them through their effects: the motion of stars orbiting an unseen mass, the radiation from accretion disks, the gravitational lensing of light around them, and most recently, the ripples they create in space-time itself. In 2015, scientists directly detected gravitational waves, tiny distortions in space-time produced by the collision of black holes. These waves confirmed the prediction Einstein made a century earlier. The universe itself vibrated as two black holes spiraled together and merged, releasing energy greater than that of countless stars. This discovery opened a new way of observing the cosmos, not through light, but through gravity. And then, in 2019, humanity saw the first image of a black hole, a shadow against glowing gas, captured by the Event Horizon Telescope. This image was not a photograph in the ordinary sense, but a reconstruction from radio telescopes spread across Earth, working together as one planet-sized instrument. The dark region in the center was the black hole's shadow, the event horizon silhouette against a luminous accretion disk. It was a historic moment, turning an abstract prediction into an observed reality. But perhaps the deepest mystery of black holes lies in what happens to information. In physics, information cannot be destroyed. The quantum state of a system should always be preserved. Yet black holes seem to erase information. Anything that falls and appears lost forever. This creates the black hole information paradox, one of the greatest unsolved problems in theoretical physics. Stephen Hawking showed that black holes are not completely black. They emit radiation, now called Hawking radiation, due to quantum effects near the event horizon. Over immense timescales, black holes can evaporate, losing mass until they disappear. But if a black hole evaporates completely, what happens to the information of everything that fell into it? Does it vanish, violating quantum mechanics? Or is it somehow encoded in the radiation? The answer remains uncertain, but the paradox suggests that black holes are keys to a deeper understanding of reality. They force us to confront the boundary between quantum physics and gravity, between the known universe and the unknown. Black holes also raise questions that extend beyond physics into the nature of existence itself. They represent regions where cause and effect become unfamiliar, where the future points inward, and where the ordinary structure of space-time collapses. The event horizon is not just a boundary in space, but boundary in knowledge. Once something crosses it, no signal can return. In a very real sense, the interior of a black hole is forever hidden from the rest of the universe. Yet, black holes are not separate from the cosmos. They are part of its evolution. In the early universe, black holes may have played a role in forming galaxies. In the far future, black holes may be among the last remaining objects as stars burn out and the universe grows cold and dark. Over unimaginable spans of time, even supermassive black holes will evaporate through Hawking radiation, leaving behind a universe that is emptier than we can truly comprehend. This connects black holes to the ultimate fate of the cosmos. They are not only objects of destruction, but markers of cosmic time. They remind us of the universe is dynamic, evolving, and shaped by processes far beyond human scales. Yet despite their darkness, black holes have illuminated some of the brightest insights in science. They confirmed Einstein's theory of relativity. They revealed the reality of gravitational waves. They challenged our understanding of information and quantum mechanics. In studying black holes, humanity has confronted the deepest limits of knowledge, and perhaps that is their greatest significance. Black holes are places where the universe becomes extreme enough to expose the seams of our theories. They show us where our models succeed and where they break. They hint that a deeper framework must exist, one that unites the physics of the very large with the physics of the very small. In a sense, black holes are cosmic questions made real. They are reminders that the universe still contains mysteries beyond imagination. And yet, they are also reminders that the universe is understandable, at least in part, through observation, mathematics, and thought. From a distance, black holes obey the same laws as everything else. They curve space-time, influence matter, and participate in the cosmic web. They are not supernatural anomalies, but natural outcomes of gravity. The universe creates them as naturally as it creates stars. In this way, black holes are not outside reality. They are reality pushed to its limit. When we look at the shadow of a black hole, we are looking at the edge of knowledge, the boundary where light itself cannot escape, and where time and space trade their familiar roles for something far stranger. The universe is vast, and black holes are among its most profound creations, silent, invisible, yet deeply influential. They remind us that even in the darkest regions of space, the cosmos continues to reveal truths about itself, and that our curiosity is one of the few forces capable of crossing the distance between ignorance and understanding.